I already mentioned that one of the limitations to having large mirrors is that when you're moving your telescope, there could be some flexure in the mirror. It can be very small, but that is enough to actually make some of the light rays converge in different locations. And therefore, the largest mirrors, anything above 4 meters, will always use this technology that is called active optics. You can see a picture. This was the demonstration telescope, and all these squares are actually actuators that are meant to be there so that when the mirror curves a little bit, they correct it back. And this is particularly important when you compare observing, essentially looking up directly versus looking at something that's very low on the horizon. And this technique, as shown here, was first demonstrated in the NTT telescope. This is the NTT telescope on my background. And then it was used for all 8-meter telescopes in the VLT, but also for all telescopes that were built after that with mirrors that are larger than 4 meters. So it is important to distinguish between active optics, which is something you use with actuators to essentially correct for any flexure of the mirror. This is a relatively simple thing to do. It's sort of a mechanical thing you do with the things you have behind the mirror. And you don't need to do this many, many times per second. So essentially, you need to correct every time you change position, and you can do it essentially by improving the focus. So these actuators will make your image more focused. The other technique that's way more fancy is called adaptive optics. That is very different from active optics, and that is not always implemented. What is adaptive optics? Well, it's essentially a technique that allows you to correct for a lot of the effects that the seeing does to your images. The way you do it, the simplest way to explain, is that you're tracking a point source, such as a star, and you're essentially trying to measure what happened to that point source. And if you do that, then you realize what sort of function you need to apply to go from the point source to that blurred image, you can try to apply it backwards. If you do that, then you're able to recover essentially your star that is much more compact. And essentially you're correcting for the effects of the seeing. The problem with this is that seeing is caused by turbulence in the atmosphere, and these effects are changing so rapidly that for this technique to work, you essentially need to be changing and deforming the mirror, something like almost 700 times per second. This technique is relatively easy if you have a star that's point-like, that's bright enough that you to track it. In order for you to use it, you need to be tracking that star all the time, seeing how that star is actually being blurred and then applying it back. And the process itself is by using Fourier transformations, but doing them very quickly and then deforming your mirror to correct for that. Sometimes there's just not enough stars to do this, so we can also create artificial stars. This is the reason why telescopes, modern ones and big ones that want to use adaptive optics, typically have lasers. If you shoot a laser through the atmosphere, then you can actually image that laser and what is happening to it and use that information to actually understand what the atmosphere is doing and then turn on adaptive optics. Here you can also see a few examples of what it means to use adaptive optics. This is what you would get without adaptive optics, just the natural seeing. And this is what happens once you're actually correcting and deforming the mirror almost 700 times per second. This is in a relatively crowded field, but this is also what happens when you look at, for example, a galaxy. You start to see the details that otherwise would be completely blurred, and perhaps even more exciting and interesting is the fact that this is the technique behind the Nobel Prize of 2020. This is how astronomers were able to actually find some stars going really close to Sagittarius A, or the supermassive black hole in our galaxy, measure the orbits and calculate the mass that is inside Sagittarius A to really establish it as a supermassive black hole and then get the Nobel Prize. New telescopes are actually planning to do this even more and even better. And instead of just using one laser or one star, these telescopes have been built so that they can actually work with something like 4 lasers at the same time. And the reason why you would want to do this is that you can then get corrections that depend on essentially the location within your image. And that is because the atmosphere is also not homogeneous from a spatial point of view. By doing this, we'll be able to further increase the resolution such that this almost 40-meter telescope will actually have the best resolution of any telescope, either on the ground or in space.